Hi, welcome to the second and last lecture of the Urban Computing Skills Lab Linear Algebra series. Let's look into a little bit more detail about a couple of very, very useful concepts in linear algebra that come very handy when we do data analysis, and we will talk about them throughout the urban informatics curriculum in various occasions. Let's remind ourselves that we study linear algebra because linear algebra provides handy ways to solve sets of linear equations. And it turns out that a lot of problems in data analysis can actually be understood as solving sets of linear equations. So for example, linear regression, finding similarity between objects, similarity between cities, or similarity between buildings, or similarity between individuals, and perhaps in a very, very complex parameter space of their medical history or their habits and preferences, as well as in image processing and data processing in general. We have already covered a few topics. We have seen what are the objects, the elements that we talk about when we talk about linear algebra. Generally, in linear algebra, we're talking about n-dimensional spaces that are populated by objects that we call vectors. Collections of vectors, collections of numbers that are multidimensional. So, for example, 2 by 3 or 4 by 6 are called matrices. And the way we want to think about matrices is as transformations or maps. They take one vector, one object of our parameter space, and transform it into another vector, another object of the same parameter space. We've also looked at different operations that can be done with vector, between vectors, between matrices, and on how matrices operate on vectors to transform the vectors. For example, to flip them, rotate them, or stretch them. So today we will continue on this theme. We will look briefly at how we solve a set of linear equations. We won't go in detail about how we find the solution of a set of linear equations in linear algebra per se, but we will look at what is sort of the interpretation the linear algebra gives us to the solution of a set of linear equations. Keep in mind that when we do this, when we cover these topics in linear algebra, some of the things are going to get rather detailed. For example, the mechanics of how we solve a set of linear equations. You don't actually do a lot of the heavy lifting by hand when you do data analysis, when you do urban informatics or any kind of data science. A lot of the functions that we describe, a lot of the methods that we described are already collected in software packages. For example, in Principle of Urban Informatics and Data Science, we generally use Python for coding. Python has very many packages that you can use to do a lot of the linear algebra and a lot of the machine learning that relies on linear algebra concepts just by simply calling those functions. But it is important that you understand what is actually being done, what is actually behind the scenes of calling scikit-learn package PCA, the PCA function. It is important that you understand what are the mathematical operations that are used to transform the data, because that allows you to move away from using these tools as a black box. And it allows you to actually knowledgeably interpret the results, understand the caveats in a result, and understand the reliability of a result. So again, this lecture will have some amount of detail. You don't have to necessarily be very handy with the operations that we do, but you will have to have an idea of what is the mechanics of these operations. So the last topic that we will address is what are eigenvectors and eigenvalues of matrices. And this is a very important topic, and we will just sort of get an intuition about them. But again, eigenvectors and eigenvalues are things that, like the dot product between vectors, come in handy, and we often talk about them with many, many machine learning algorithms. Okay, so let's get started with sets of linear equations and solving sets of linear equations. Let's remind ourselves, first of all, that we have already looked at an equation. We have looked at the equation for a line in a two-dimensional parameter space. So we have a space of x and y defined by this coordinate system. And we have a line well, we have an infinite number of lines in this space. We have a particular line which we're looking at, which has some direction. The direction is given by the angle that the line forms with the x-axis. And so this angle is a function of the ratio of the length of the x-axis and the y-axis in a vector that runs along this line. And it doesn't, the details of how you obtain that angle don't matter. It's an arctangent function, which is a trigonometrical function. But the point is, as long as the axis ratio for any point on the line remains constant, the angle doesn't change, and the direction of the vectors don't change. So this is, in fact, an equation for a line. In that particular form, y over x equal to 3, we generally write it in this form, which is a little bit more intuitive, 3x plus y equal to, in this case, 0. Notice that here we have a 0 because this particular line passes through the origin. The origin is the point 0, 0. And let's look at this equation in a little bit more detail. What that equation says is that when x is 0 when I'm on the x-axis, and y is 0 when I'm on the y-axis, the point that I'm describing is 0. There is no offset. This, for example, is a line that is parallel to the previous one, so it has the same alpha angle, the same axis ratio for any vector on this line. However, it is at an offset from the origin. So let's look at a system of linear equations. So a system of linear equations is a set of equations, much like the one that we looked at before. What is linear here? What does the word linear refer to? The word linear refers to the fact that the unknowns, which in these equations are the values of x and y, come in the equations only in a linear form, which means to the first power. There's no x squared, there's no square root of x, there's no function like exponential of x. So the only way in which we see the unknowns in these equations is to the first power, at just linear as x and y. So then, as long as that is preserved, any set of equations that looks like this is a set of linear equations. In this case, we're talking about a set of linear equations in a two-dimensional space because we have two unknowns, x and y. Of course, this can be a lot more complicated, and we can be in very highly dimensional parameter space and have similar equations that would look like ax plus by plus zz equal to d, etc., etc. There is a very important rule that we're going to look at when we talk about sets of linear equations. Right now, I'm just going to tell you the rules, and we're going to look at it and take it as a rule. However, towards the end of the discussions about solving sets of linear equations, we will have a motivation for it and a more intuitive understanding. For right now, let's just look at it. It refers to the number of equations compared to the number of unknowns in the set. So the number of equations, obviously, in this set is 2. I have one equation here and one equation here. The number of unknowns is also 2. I have x and y. Those are the parameters that I'm looking for. So we want to compare the number of equations and the number of unknowns in a system. If I have more unknowns than equations, so say if one of these equations was, instead of being as it is, was 2x minus 3y plus z. If I have more unknowns than equations, then that set of linear equations has multiple solutions. In fact, there is an infinite number of solutions that satisfy those conditions. If, on the other hand, I have more equations that are known, say that I add an equation to this set, 3x minus y equal to 4, then I have more equations that are known. The problem is over-constrained. That typically will mean there is either a single solution if the equation is complying to the set, but then one of the equations is superfluous. It's just in fact, the same as one of the other equations, maybe multiplied by a factor for all arguments, for all elements of it. But in some instances, it will just be an unconstrained problem. It will just be a poorly phrased problem. It will not have a solution at all. What I want to be is situations in which my number of unknowns is equal to my number of equations. So if I have 2 equations, I need to have 2 unknowns for the problem to be phrased correctly. That is a problem that has a single solution, and it always has one solution. So in this case, I have two equations and two unknowns, x and y. So this is a well-phrased set of linear equations. So how do we solve it? Let's go to the whiteboard and remind ourselves how do we solve it. This is really, there are ways to solve these sets of linear equations that really rely on linear algebra, but they're a little bit more complicated, and we won't go over them today. I just need us to remind ourselves about how one would go most trivially to solve this set of equations. And we're going to do that, in fact, by substitution. Let's rewrite the equations on the whiteboard. 2x minus 3y equal to 34. And 4x plus y equal to 12. So to do it by substitution, I'm going to choose one of the unknowns, whichever one I like best. And I'm going to express it as a function of the other unknown. So I'm going to bring one of the unknowns from one side of the equal to the other side. In this case, this equation is the easiest one to work with because I already have y without any factors in front of it, so I don't need to do any divisions. So I'm just going to bring 4x to the other side of the equal sign, which of course will change its sign. So y is equal to 12 minus 4x. This is the same equation as above. So once I have this y, I can plug it into here and rewrite that equation as 2x minus 3, 12 minus 4x, which is my new value of y, equal to 34. This is y. Now I have one equation with a single unknown, so I can solve this. This only has one solution. 2x, it's just going to require a little bit more massaging to get the solution out of it. 2x minus 3 times 12, which is 36, minus times minus is plus, 12x is equal to 34. I have two terms in x. I'm going to put them together. 14 times x is equal to 34 minus 36. So my new equations are 14 times x is equal to 70. And then I still have y is equal to 12 minus 4x. This gives me x equal to 70 over 14, which is 5. So my first unknown is equal to 5. And then I can plug this information back into this equation, and I have y is equal to 12 minus 4 times 5, which is 20, which gives me minus 8. So the other unknown takes the value of minus 8 in this set. So we didn't use any linear algebra to solve this equation. We can't. We can, though. We could if we wrote it in the form of a matrix. So you have the step of the equation of the solution in the slide. But let's look at it from a linear algebra interpretation point of view. I can write that set of equation, the same set of equation, in a matrix form. I'm going to write the matrix with the coefficients and separate it from the vector with the unknowns. So I have a matrix that contains 2, minus 3, 4, and 1. This is this piece. And I have the unknowns in a vector, x and y. And I also have a vector, which is the result. So what this, in the linear algebra terms, what this is saying is that there is a matrix that applied to a certain vector will transform that vector into this new vector, 34 and 12. Let's draw it on a two-dimensional plane, because with linear algebra, we've seen that we can actually draw vectors. So let's draw the pieces. The first thing we're going to do, let's look at what is the value, what are the easiest value that we can draw on this plane that satisfy that equation. Let's look at the second equation. What happens to 4x plus y equal to 12? And at this stage, I still don't know what x and y are. What happens when x is 0? Because this is an equation of a line, it describes an infinite number of points in my parameter space. And for one of those points, x will be 0. So we drop 0. We drop this factor here because x is equal to 0. What I'm left with is y equal to 12. So one of the points that satisfy this equation and belong to that line lives right here at x equal to 0 and y equal to 12. Let's go on. Let's pretend that let's see what happens when y is equal to 0. Then I have 4x over 12. So when y is equal to 0, the value of x that satisfies this equation is x equal to 3. So now I have 2 points, and between any 2 points in a two-dimensional parameter space, I can draw a line. Then I can do the same trick for the other equation and find the 2 points, the easiest 2 points, the one where x is equal to 0 and the one where y is equal to 0, and draw a line between them. The solution of the set of equations is the point where these 2 lines meet, which in this case happens to be 5 minus 8. So we found the solution in a sort of graphic and intuitive way. The solution of a set of linear equations is the single point in the parameter space where the vectors described by those equations meet. So in a two-dimensional space, this means a point where 2 lines meet. And 2 lines always meet in a single point if they're not parallel to each other. But what if I go to higher dimensions? If I go to higher dimension, if I go to a 3-dimensional parameter space, then my objects will be planes. And 2 planes don't meet in a point. They meet in a line. That's why I need a third plane to find that single point that is the solution of the set of linear equations. That's why we have a rule that we need n equations for n unknowns. Okay, so that's enough for solving linear equations. Again, there are efficient ways to do that in linear algebra. There are more efficient than the way that we went about here. You will very rarely have to do it by hand. Most likely, you will just call some Python or R packages, and the equations will be solved for you. But you need to understand that this is what's being done behind the hood. The last topic that we're gonna address is eigenvectors and eigenvalues. Let's look at it from a graphical point of view once again. So again, we're in a two-dimensional parameter space where vectors are collections of 2 numbers that describe a point. In this case, the vector 2, 3 that describes this point. And I'm going to draw it both as a point and as an arrow that origins at 0, 0 and ends at the point, at the location of 2 and 3. Let's also use a matrix in this space, an arbitrary matrix in this case. Let's pick a simple one that is 1, 0, 5, 0, 5, 1. And because matrices are effectively collections of vectors, we can think of this matrix as one column vector and then another column vector. I can also draw them just to give an interpretation of what they look like. And this would be a graphical interpretation of that matrix in this parameter space. The next thing we're going to do, let's multiply the matrix by the vector, thus transforming the vector, because as we discussed, matrices are transformations that take vectors onto other vectors of the same space. So if I multiply this particular matrix by that particular vector, I obtain a new point in the space, 3.54, which is represented by this point and by that line. And okay, we've already covered this and we're already familiar with this. Let's consider a different matrix, but the same vector. Let's consider this matrix, which is 1, 2, 6, and 0. So let's see what happens when we apply this particular matrix to that vector. We're going to multiply the first row by the vector, so 1 times 2 plus 2 times 3, and the second row by the vector, so 6 times 12, and 3 times 0. So we obtain 8 and 12. But 8 times 12 is also equal to 4, the scalar 4, the constant 4, times the same vector. So we have a matrix that acts on this particular vector as a simple scalar would. If we look at it graphically, what happened is that the matrix applied to this vector functioned as a scalar. So it simply stretched the vector. It made it longer. It may have made it shorter in other circumstances, but it didn't rotate it. It didn't change the direction of the vector, it only affected its magnitude. For every matrix, if there exists one such vector, that when the matrix is applied to that vector, what happens is simply a stretch and no rotation. That is called an eigenvector for that matrix. So a vector V is an eigenvector of a matrix if there exists one particular lambda, which is a constant, such that the matrix times the vector is equal to that constant times the vector. Then lambda is also referred to as the eigenvalue of that eigenvector. Just incidentally, eigen means self in German, and or proper, or one's own. Again, we want to give a more intuitive interpretation to this concept. We can look at a graphical interpretation, which is the following. And for any transformation A, the vectors that once I apply that transformation describe points that can be joined by a single line to the origin. So if all the points, the original point, the transform point, and the origin lie on the same line, that is an eigenvector. And the amount, the magnitude change between the original vector and the transform vector is the eigenvalue. And once again, that means that the vectors are only stretched and not rotated by this transformation. Every point in this line, by the way, every vector that lies on this line will itself be an eigenvector for the same matrix. And altogether, the line where all of these infinite number of vectors lie is called an eigenspace. So there are the reason why we like to discuss this is because these vectors represent the easiest way to talk about this transformation. If I can change the basis of my space, if I can change the coordinate systems of my space, from this x and y coordinate to an x and y coordinate that lie parallel to that eigenvector, and if it happens that there is a perpendicular eigenvector that allows me to create an actual coordinate space of orthogonal coordinates, then I have a very easy way to describe what the transformation is. I'm going to give you one single application for this concept, which is a very common analytical method for data, which is called principal component analysis. And I'm going to do that in an IPython notebook. At this stage, all I want to do is give you an example of an application of a linear algebra method, of a linear algebra algorithm to data science. Principal component analysis is a very, very common linear algebra method that is very commonly used in all sorts of data science disciplines. And it is extremely tightly close to the actual linear algebra method. What it comes down to is finding the eigenvalues and eigenvectors of a space of objects. In this case, we're going to use images, portraits of faces. And the usefulness of it is there are many applications. It allows you to compress the data by finding what is common to all the objects in your data set and what is peculiar about each one of the objects. And you can set a threshold at which you decide the accuracy is sufficient, and then you can describe your objects with a subset of the data. In this case, it's used for facial recognition. We will build eigenvalues in a space of images of faces, of portraits, and through the understanding of what is common to all faces and what is peculiar about one face, this method allows to do quite accurate image recognition. At first, I'm gonna, here you have some references. This is a reference to the original paper. This is a reference to the Rice eigenfaces group, where you can find more details about the algorithm and some of the math. But again, you don't need to know the math at this stage, although it is important that you understand what is the math behind an algorithm so that you don't use it as a black box, that you understand what is happening actually behind the hood. You are going to be actually applying the algorithm simply by importing a package in Python or R or whichever language you're using, and running a few lines of code, writing a few lines of code to apply the machinery to your data. The packages will do the hard work for you, but it is again important that you understand what work is being done to understand to actually interpret the result. So let me import a few packages. I'll import the NumPy library, which is a library that allows me to work with numerical arrays of numbers. The Pylab library, which is the library that we use to plot. Pill, which is the Python image library, I'm also importing. This library allows me to work with images so that I can load the portraits in and turn them into arrays of numbers to then use them with NumPy or scikit-learn, as we will see. So the first thing I'm going to do, I'm going to load the faces into memory. This will take a second if you download the notebook and do it for yourself. But this is the result. These are faces of the current cohort of CUSP students. There's 81 portraits. Notice that the portraits originally are a little bit more than the face. They start at the waist, so I'm going to crop them. The place where I'm cropping them is here. I'm going to choose a width and a height of 80, a width of 50, and I'm going to choose the relevant region of the image that I want, which selects more or less just the face of the students. Also notice that images are typically three-dimensional objects. So when I store an image in the memory of a computer, I have 3 numbers for each pixel. Those represents the colors of the image, the R, G, and B channel. So each one of the pixels in the image, each location in the image, is expressed from the point of view of a computer as a series of 3 numbers, how much red, how much green, and how much blue I have. In this case, I don't care about the colors, so I'm going to take the average by calling .mean on that axis, on axis 2. I'm going to take the average of the 3 colors. So each image is now a 2-dimensional object, which has at each position, at each pixel, at each x and y coordinate, a single number. The next thing I'm going to do, I'm going to normalize the faces. We don't have to go into details as of why I'm doing that right now, but what I'm doing, I'm taking the average face and I'm subtracting it from each portrait. This allows me to put all the data into the same frame of reference. Here you have the average face, the mean face for my data set, and here you have some of the portraits after I subtracted the mean face. Basically, this tells me how unique a face is compared to the average. Now, what I really want to do, the images are organized, image files are organized into rows and columns. This is because we want to perceive them as 2-dimensional objects. When we look at the word, we look at a 2-dimensional map of what we see. So we want to be able to perceive those images as points in a 2-dimensional space. However, the computer doesn't care about the fact that the images are arranged in rows and columns. So what I'm actually going to use for the principal component analysis is a flattened version of the face, where every row is basically attached to the end of the previous row. So it's a single string of object instead of being a 2-dimensional object. So my new array that I'm going to use goes from a dimension of 81 for 81 images, 80 for 80 pixels height, 50 for 50 pixels wide, to a dimension of 81 for 81 images, and 4,000 numbers, 4,000 being 80 times 50. So I've simply flattened out the images. Now they're better objects to work with from the point of view of a computer. Now here is where I run the PCA. And notice that all I need to do after all the math that takes to do this process is actually going to be done for me by the scikit-learn package. I'm loading a single package, a single module inside of the scikit-learn package. Scikit-learn is a common Python package to do machine learning tasks. I'm loading scikit-learn decomposition PCA, importing the PCA module, and I'm applying it to my data set with this line of code. So again, all of the math that it takes to find the eigenvalues and eigenvectors of a space is done for me by scikit-learn, and all I need to do is write 2 lines of code. This xvar is a variable that contains essentially,
a number that corresponds to the importance that each eigenvector has in explaining my parameter space. And the way the eigenvectors come out of this package is ordered, so that the first eigenface, the first eigenvector, is the one that is describing the data set best. The second one described it the second best, etc. And the way I want to visualize it, I'm going to plot that number in the order in which the eigenvectors are come out of my scikit-learn package. I'm going to plot how important they are in describing the data set in a cumulative way, so that each number represents how well all the eigenvectors up to that one describe the space. So the first eigenvector describes 20% of the space. The second eigenvector and the first eigenvector together can explain 33% of the space, etc., etc. Now let's take a look at those eigenfaces, the eigenvectors of my parameter space. These ghostly images are my eigenvector. They're generally called eigenfaces, and effectively they represent what is common to all the faces in my dataset. And you can recognize some features. You can recognize the hair, you can recognize the eyes, you can recognize in some of them at some point glasses start popping up as an important element in the description of some of the objects in my space. Again, at the top, I'm plotting a number that corresponds to technically what we refer to as the variance in the data set explained by components up to that one. The first component explains 20% of the variance, and the second component explains 33%, the second and first component together can explain 33% of the variance, etc. And I'm plotting up to 90% of the variance explained. Now I can use these images to reconstruct images in the data set. The first image that I'm plotting here, I'm plotting 4 images. The first one is one of the images, one of my data points, one of the images in my original set. And then I'm plotting the same image, however, just this time reconstructed through the eigenvalues and the eigenvectors. I'm plotting the image reconstructed using all the eigenvalues and eigenvectors. Now, these should be identical to the original image, because if I use all of my eigenvectors, I can express any point in my parameter space. And then if I use only some of the eigenvectors, I can reconstruct the image to a lesser fidelity. Here using only the first 10 components, here using only the first 33 principal components, I get a less faithful reconstruction of my image. But you see how perhaps if fidelity, if an approximate reconstruction of the image is all I care about, then I can throw away some of the data and compress my data set and save storage space, but still maintain most of the information. The values associated with the eigenvalues represent what is peculiar about this space, and they're the method through which people use PCA eigenfaces to identify individuals in images. Notice that when I looked at my original data set, I mentioned that the cropping, the process through which I was selecting only the face out of the portrait, was rather rough. I simply selected a portion of each image where generally the face is located. This data set has an issue for this purpose, which is the fact that the faces are not aligned. And the secondary issue is that hair are shown in all of the faces. And the hair end up being a very, very important element in describing how peculiar one face is compared to the set. If I wanted to do this work more seriously, I would align the faces so that what I'm seeing, what is a change between an image to the next, really has to do with what's peculiar about that face and not with the position at which that face is portrayed. So here is the same process done with a dataset that was constructed for this purpose by the Rice Eigenfaces group, which collected images of the members of the group. And notice that the images are sometimes of the same member, that have members having being portrayed with different facial expressions. So this is a better dataset that really shows what is unique about a face and the facial expression vectors. Now, these should be identical to the original image, because if I use all of my eigenvectors, I can express any point in my parameter space. And then if I use only some of the eigenvectors, I can reconstruct the image to a lesser fidelity. Here using only the first 10 components, here using only the first 33 principal components, I get a less faithful reconstruction of my image. But you see how perhaps if fidelity, if an approximate reconstruction of the image is all I care about, then I can throw away some of the data and compress my data set and save storage space, but still maintain most of the information. The values associated with the eigenvalues represent effectively what is peculiar about this space, and they're the method through which people use PCA eigenfaces to identify individuals in images. Notice that when I looked at my original data set, I mentioned that the cropping, the process through which I was selecting only the face out of the portrait, was rather rough. I simply selected a portion of each image where generally the face is located. This data set has an issue for this purpose, which is the fact that the faces are not aligned. And the secondary issue is that hair are shown in all of the faces. And the hair end up being a very, very important element in describing how peculiar one face is compared to the set. If I wanted to do this work more seriously, I would align the faces so that what I'm seeing, what is a change between an image to the next, really has to do with what's peculiar about that face and not with the position at which that face is portrayed. So here is the same process done with a dataset that was constructed for this purpose by the Rice Eigenfaces group, which collected images of the members of the group. And notice that the images are sometimes of the same member, that have members having being portrayed with different facial expressions. So this is a better dataset that really shows what is unique about a face and the facial expression. And so if I redo this process with those images, I obtain eigenfaces that are more recognizably related to faces, to portraits. This is the mean face for that data set, which again is more closely resembles an actual face. I'm doing the same thing that I did before, flattening the images, applying the PCA with a call to scikit-learn package. And here are the eigenfaces generated with the new dataset. That's it. This was just simply an application of a linear algebra method to computer vision in this case. And it's just to give you an idea of how simple in reality it is to apply these algorithms, how you can apply them with a single call to a function, and how powerful they are. Please take a look at the details of the notebook. There's a lot of things that we will go over in the classes. For example, how to read and manipulate images, how to operate on arrays, to rearrange them, and of course, how to make simple plots. And that's it. Thank you very much, and I will see you in the fall.